In this video lecture, I will try to explain the requirement of base, sub-base and subgrade of a pavement layers. So by requirement, I mean that what are the properties we need to design pavement. Okay, so again, what is base layer? Base layer is aggregate layer, unbound. We bring some good quality with good gradation aggregate, place it there, compact it. Sub base is little inferior, not as good as base, little inferior. Then my natural soil. So when we design pavement, what are the properties we need for this base, sub base or subgrade? We need two kinds of properties. One is the physical properties like gradation, soil type or aggregate type, and the void ratio, the flat and elongation ratio, Los Angeles aberration value. So many physical characteristics. And then we need mechanical characteristics. What is mechanical? Mechanical means if I apply load, how much it will deform or how much it will resist, that kind of mechanical. Simply, it is modulus. Modulus. We need modulus of this material. Now, so physical properties like gradation, gradation means like sieve analysis, like soil classification, ASTO, A1, A2, A3, you saw this is. So physical characteristics, you already covered it in your previous classes. I know that before taking this highway or pavement design class, you took soil mechanics class, you took concrete material class. So you took like two classes on soil and aggregate. So I'm not going to the physical characteristics. I'm going to the mechanical characteristics. Mechanical. So what is the mechanical characteristics or properties? The main property we need is modulus. What is modulus? If I write the equation, so E did I no, it is not that, it should be here. So epsilon here, yeah. It is strain, it is stress, it is modulus of elasticity. You saw this equation in your strength of material class also. No, I made a mistake again. So it is this, the strain is this, opposite, yes. So if my modulus is higher, you can see my strain will be lower for a particular applied stress. So when my traffic will go, it will apply some load that will produce some stress, that is fixed. Now, whatever I apply here, if my modulus here is higher, my deformation of this layer will be lower. So we need to know the value E. Now, this equation is right in strength of material class. This equation does not apply to pavement. Why? In that test, you took a steel sample like this and pull it monolithically, pulling, suddenly failed. It's a static type load, slow load, and you are monolithic, you are continuously increasing. For pavement, the load doesn't apply like this, yes? If you think about it, how the wheel is going very quickly. If your speed is say 70 mile per hour, 70 mile per hour, how much time your load will be applied here? Very few millisecond. Even not few, fraction of millisecond, fraction of millisecond. So load will come, go very quickly. So those kind of test doesn't work for soil or even aggregate base. I'm talking about all of this, yes, all of this. So what we do here, we do resilient modulus. Resilient modulus, it's a new term to you, maybe you never heard about this term before this. Is now modulus different types. The typical modulus you know is Young's modulus. Take a sample, pull it or push it monolithically, slowly, and then you will measure stress, strain, and the initial slope is Young's modulus. other kind of is resilient modulus. You will hear another kind of modulus in when we will talk about asphalt material, the modulus of asphalt, that is called dynamic modulus. So we will talk about dynamic modulus later. Now resilient modulus. What is this? What does resilient means? Resilient means elastic, like whatever, if we apply some load, it will deform, after applying, it will come back. So that kind of resilient, elastic modulus is called, it has a special definition, I'm explaining here. So we represent by MR. MR means resilient, M means modulus. What is that? Cyclic stress divided by so cyclic stress divided by cyclic strain. Let me see the symbol we use. I think it is epsilon R. Epsilon R. What is this? Cyclic stress. Now you have to remember S. For stress in strength of material class, we use sigma. In reinforced concrete design class, we use lowercase f. Okay, again. So stress. We use sigma in strength of material class. Strength of material class. We use lowercase f in concrete. We use uppercase f in steel design. Now we are using S for soil. So same thing, yes, stress, but same thing, we use different symbols in different classes. So make sure that you know, you are familiar. It is cyclic stress divided by recovered strain. Yes, R means resilient strain or recovered strain, whatever you call. Now, what is cyclic stress? Cyclic stress is whatever cyclic load you will apply divided by area. Now, before starting cyclic, so what we do here, we apply load. So we prepare a cylindrical soil sample. Say if height is typically 2 times of the diameter. If my diameter is 4 inches, height will be 8. If the diameter is 12 inches, 6 inches, height will be 12. So this we prepare a cylindrical sample, place it inside a confined chamber, apply cyclic load under defined confining pressure. Okay. If I remove this, so again we are talking about resilient modulus. What we do here, we prepare a cylindrical sample, place it under a cylinder, then we apply confining pressure, then we apply cyclic pressure. So we apply cyclic pressure here. Now, why do we apply confining pressure? Because if my pavement say here, so we are talking about my material here, load is here. So this soil has some confining pressure, yes, some confining pressure, yes? And vertical pressure, both. So a soil here, a soil here, a soil here. Every soil doesn't have the same confining pressure. So we simulate that also. We test. This is our soil sample. All right, here. This is our soil or aggregate, whatever it is. So we apply different confining pressure and different axial pressure. So it is cyclic. Now, what is the cyclic? We apply Haversine load. So my load application is similar to this. Triangular, then this. We apply this kind of load. It's called Haversine, Haversine. Haversine. The load duration is 0.1 second and there is a gap 0.9 second. So we apply Haversine type of load. Load applied, goes, applied, goes, but there's a gap. Load applied, goes, wait for 0.9 second, load applied, goes, wait for 0.9 second, load applied, goes, wait for 0.9 second. So this way, yes. So we apply load in 0.1 second and wait 0.9 second. So we apply like very quickly, then stop, very quickly, then stop, very quickly, then stop, very quickly, then stop. So this way we apply this load. And then we calculate the load applied over area is our cyclic stress, and then we measure the deformation of the sample. Deformation, we place some sensor here, or we place some sensor here also, depending on the device you are using. Sometimes we use the sensor here to measure the deformation, sometimes here, depending on which sensor you are using. Okay, so we got cyclic stress, then we calculate cyclic strain. Yes, what is that? It is E by R divided by original length. This is deformation, this is original length. It is similar to testing a steel specimen. Apply load, measure stress, measure strain, take the ratio. Similar, but here we apply so many cycle, 100 cycle for a particular confining pressure and particular cyclic stress. And in the last 5 cycle, we take the average cyclic stress, average cyclic strain. Ratio is resilient modulus. So hopefully you understood what is resilient modulus. If I summarize, we take sample and compact it in our laboratory, make a cylindrical sample, whatever the diameter, length is twice, place it inside a chamber where we can apply defined confining pressure and defined cyclic pressure. For a particular pressure, so we apply cyclic ever sign load. We'll apply load in 0.1 second and take a rest 0.9 second. This way 100 cycles for a particular stress configuration. Then we get we calculate the cyclic stress at the last 5 cycle. We apply this kind of load 100. Apply 100, take the last 5 cycles. Why last 5 cycles? Because first at the beginning the result is not so like stable. It changes because soil is not a homogeneous material. That is a different story. Did I forget anything or something else also? Then once one configuration is done, in next cycle we take another confining pressure and another cyclic pressure as recommended by ASTRO. So this way we determine the resilient modulus. Now this is the main input property for designing pavement. This is the main design input property for soil, aggregate or aggregate layer. And so yes, I think I covered everything. In the next video I will talk about similar mechanical properties. So let me stop here to make the video length is shorter.